Bismillahirrahmanirrahim. Welcome to lecture number 7 of the data science course. We will discuss the series data structure. We will discuss series data structure and we will see how this series data structure can be used in Pandas library. So let's go to our Jupyter notebook and see how to use series data structure. So this is our series data structure. First we have some requirements in case some library packages are not installed on your system, so you need to execute this command to make sure that all libraries are installed. Since we have already performed this operation in this notebook, so there is no need for this one. Let's start from here. So we will explore the Pandas series structure. By the end of this tutorial, you should be familiar with how to store and manipulate single-dimensional index data in the series object. The series is one of the core data structure in Pandas. You can think of it as a cross between a list and a dictionary. The items are all stored in an order and there is label with which you can retrieve them. An easy way to visualize this is two columns of data. The first is a special index, a lot like keys in a dictionary, while the second is your actual data. It's important to note that the data column has the label of its own and can be retrieved using the .name attribute. This is different than with dictionaries and is useful when it comes to merging multiple columns of data, and we will talk about that later in the course. So let's import Pandas to get things started. So we import Pandas as PD, and this is just to know about the definition of series, but let me disable it. We don't need it. So I can run this one, and this one is, let me bring it to the, so Pandas is imported. Then we create a list. Let's say we have animals and we have tiger, bear and moose, and to create the series data structure we can simply execute pd.series animal. So let me clear this one. We clear all the output and let's start from here. So we run this one. Panda is imported. Then we have animals data structure and let's run this one. So it has indices 0, 1, 2 and elements are tiger, bear, moose, and the data type is object. So you can see that we can create a series by passing in a list of values. When you do this, Pandas automatically assigns an index starting with 0 and sets the name of the series to none. One of the easiest ways to create a series is to use an array-like object like a list. For example, you can see a list here and its list is actually something is wrong. Okay, so we have numbers 1, 2, 3 and pd.series numbers, and if I run this one, it creates 1, 2, 3 with the index 0, 1, 2, and you see the d type here is object because we are passing strings, but here it is integer 64. So series is the top level or a module function, and we pass in these animals or numbers, and the series the result is a series object which is nicely rendered to the screen. We see here that the pandas has automatically identified the type of data in the series as object and set the d type parameter as appropriate. This is what we have seen here and here. Now we can do another one like this. So we have animals, tiger, bear and none. So none means that we have not new object, and we create its series as this one. So you see it's tiger, bear and none, and the d type is object. D type means data type. We can use for numbers as well. So we have 1, 2 and none. Remember, here we are using string and then we use none as object. Here we are using numbers, integers, and if you can recall, here we use these numbers and its d type is int 64. So when we create this one, let's try to execute. Oh, it's something different. You see it's 1.0, 2.0 and nan. Nan means not a number, which is different than this one. Here we created string and we pass it none, so the object is none. Here we pass a none, but here the numbers are passed. And if you notice, here the d type was int, here the d type was object, but here the d type is float 64. So this is different than this none. We can compare this one by importing numpy as np and np.nan equal none. We want to compare whether nan is equal to none. If they are equal, it should return true, otherwise false. So it returned false, which means that none and none are different. We can see np.nan equal np.nan to compare whether they are true or not. So the answer is false. How we can see the missing value? So np.isNan, np.nan. So we can compare this using isNan and it returns true. So this is important that you understand the how to fill missing values, because if you fill missing values with none, it's different result, and if you fill it as np.nan, it's different result. Okay, so let's go to the next one. Mainly these are efficiency reasons. We will cover these topics in later examples when we see how to fill on missing values as a nan and as a none. So let's go to the next one, and instead of creating indices, instead of allowing series to create indices, we can create indices by ourselves. So for example, here we have some game names and here the country names, and we create pd.series sports and we print s, and we can do like this, and you see instead of indices starting from 0, 1, 2, we have indices what we have created, same as dictionary. So archery, golf, sumo and taekwondo, and it's an object, the data type is object. We can print s dot index, and you see it can print these indices, and its d type is object. Let's create a new series as tiger, bear and moose, and the indices are what we create here. So we can do like this, we create a dictionary and pass it to the series data structure, or we can create like this, one list and index with another list, and if we execute and print s, it's the same as above. Now let's try to understand this other example. So we have the same data, but we are using the one with the sports, but we are using this index. So we are using golf from here, sumo from here, and hockey, but hockey is not in the list. So let's see what happens when we create this series data structure. So golf, Scotland, it's taken from here, and archery is not taken, sumo is taken, the next one from South Korea is not taken, but PVC hockey is not a number, and its d type is object. So what I'm trying to explain, if you do not have the index for a data, so pandas create index and its values automatically. You don't need to provide the full data. Okay, so let's continue this series data structure. We will discuss how to query a series. So let's say we have sports dictionary, and where we have this data, and then we create this series. So it creates this series structure. There is an attribute ilog. Ilog means that what is at position 3. So if you print ilog 3, it prints South Korea, because this is position 3. Remember that in Python indexing start at 0. So this is 0, 1, 2, 3. And we can do with the name as well as .log, and simply Scotland. We can do the same. Instead of ilog, we can use this S3, and maybe I need to do like this. So S3 print South Korea, the same as ilog. So no need for this attribute. Or we can do simply sgolf. So no need for using this log. Remember, this ilog and log, they are attributes. That's why we are not using parentheses. These are not methods, these are attributes, and these indexing operators is used. But it's very tricky to use this notation. Here in this case it's not this easy because we are using position 3 because the indices are strings. But let's create another example where indices are numbers. So we create this spores 99, 100, 101 and 102, and then we create this series data structure. So if we execute this one, the indices are numbers. Now if I use this one, like if I'm not using ilog and I say S0, let's see what happens. Oh, there is an error, and it basically says that it cannot find the key with 0, and if you look to the data there is no key 0, although this is position 0, but we do not have, so Python cannot differentiate in this case between index 0 whether you intend to use ilog or you intend to use position 0. To deal with it, it's important that you use ilog. So if we do ilog, let me do it. S.ilog 0 and give you this one. So let's create another series with numbers, and we want to compute the average of this series. So we have Panda series, pd.series 100, 120, 101 and 3. It's S, and these are float numbers, and we want to sum them, so total equals 0 for item in S, total plus equal to item, and print total. So this is how to compute total. You can compute average by dividing on length S. This is the average. But let's, I think the example is for total. So we can use vectorization, and vectorization is a very important concept in data science. Vectorization means that the underlying parallel processors, they are utilized, so you don't need to write extra code to parallelize your code on the parallel processors or on the GPUs, but you can use NumPy. So NumPy is a library, and that allows us vectorization. So we import NumPy as np, and we do simply np.sum, and we can print total. So it's the same results as above. You can compare both the results, both are the same. Now what's the advantage of using this one? One advantage is it's simple, you don't need to write this bulky code, and another advantage is the speed. So let's try to understand by creating a series data structure of some random integers. So np.random rand integer from 0 to 1000, and how many numbers we create? We create 10,000 numbers. So let's try to print s.head. S.head will print the first 5 numbers, so 0 to 4, and you see these are some random numbers from 0 to 1000. We can confirm its length, so there are actually 10,000 numbers, and we want to sum these numbers by using this timeit function in Python. So if you use this %timeit, it will run the code in this cell for, by default it's 1000 times, but we can change it, and we say that this loop happens let's say 100 times because we are recording this video. So we create summary 0 for item in S, summary plus equal to item, and let's see how much time it takes. You see it's taking some time, and in total it took 2.92 milliseconds. But if you use the NumPy function np.sum, the way we use here, so we use the same structure, but we say np.sum, and you see it's faster because it's 308 microsecond. Here we are talking about millisecond, and here we are talking about microsecond. So you can understand that this is much faster than this one. Here the speed up is not significant because we are processing just 10,000 numbers. So 10,000 numbers can be processed in milliseconds. But imagine we are processing millions and billions of code per loop. So then this function it takes advantage of the parallel architecture. And this NumPy, we can simply perform the let's say we want to change all the numbers by 2, so we can do s plus equal 2, and we print the top 5 numbers. So you see the top 5 numbers, it was 484, and all the numbers are added by 2, so it's 486. And if you can compare the other values, you can see all the numbers are increased by 2. Now the non-vectorized version would be something like this. For label, value in s.iterate items, s.set value, label, value plus 2, s.head, and it will perform the same operation as above. So you see all these values, they are updated by 2. And remember that in new version of the Python, this set value is changed to atr.iat. Okay, so you may see that, well, I don't see any difference between the two, so we can compare. So we do this one. Let's time it for 10 loop, and we create the same series from 0 to 1000, some random numbers of 10,000, and we add all the element, and we time this one, and we do by this one. So let's see how much speed up we get. You see it is executing. This static means that this cell is executing. So it's taking some time because we are adding all 10,000 numbers by 2. It's still executing. Still it's taking time. I mean, it shouldn't take this much time, but I think it's better to interrupt it and we execute this for one loop. Maybe it takes less time. So the loop is happening 10,000 times. We just started the second one as well. Let's hope it completes soon. Well, still it's taking a lot of time. Let's try to interrupt and maybe we create, let's say just 100 elements. Maybe it takes less time. Okay, let's do it a little more because it's 84 milliseconds. I just want to demonstrate how Python helps us. So it's 557 milliseconds. So let's do it with 1000 for one loop. So it's same number, you can compare from here. And we do s plus 2. And let's see. So it's 557 milliseconds. And this is just 1.73 milliseconds. So this is how you can see that how NumPy library use vectorization. It uses the underlying parallel processing and it gives us speedup. Let's see this example, pd.series 1, 2, 3. These indices are, if I remove this one, and you see the indices are 0, 1, 2. But now I add another one, let's say s.location animal bears. And then you see the next index. So index not necessarily need to be integer in pandas. It can be objects. So here we have 0, 1, 2 and animal. And let's say this is another example. We have original spores. This is series and it has these countries and spores. And we have another one, cricket loving countries. So we create, let's say Australia, these other 4 different countries, and all they love cricket, right? So 4 different countries with the index cricket. This is different game name, this is country name, so we create cricket as index, and then we can append. So original sports dot append cricket loving countries, and we create it to all countries. So nothing happens, but if we print original sports, this one is printed, and if we print cricket loving countries, so then cricket, 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 cricket 4 times to all countries. So you can see the index is basically repeating. This is what we want to demonstrate. And if we do the all countries, so you see it's the original countries list plus the cricket loving countries. And if we do all countries.log cricket, it should give us all the countries with the index cricket. So it means that we can repeat indices in pandas library. So I think for now this is enough. We discussed the series data structure and we see how to use NumPy vectorization, and we see how to use indices and how to query this series data structure, and different operations are demonstrated. Thank you very much.